Hi guys, welcome to the session. This is Rajshekhar from St. Peter's Engineering College. Today we are going to discuss about the k-nearest neighbor algorithm. The k-nearest neighbor algorithm is it's a classifier. Also in the classification books we have a k-nearest neighbor algorithm there. So we will discuss about the k-nearest neighbor classifiers very clearly in this session. Let's start our session. The k-nearest neighbor was this method was first discovered in the early of the 1950s. In the 1950s, we don't have that much of the computing power, so the neighbor algorithm will not be that much of popular in those days. After this method, the method is a labor intensive when the large training data sets are available, and it didn't get any popularity until the 1960s. After the 1960s, the computing power became a more so, and it became the increased by the level by level, and since it has a since widely used in the area of the pattern recognition. So it's mainly using in the recognition of the patterns which are related which are nearest to that particular process and the data tuples. So nearest neighbor classifiers are based on the learning by their analogy. So it is by the comparing of the given test tuples by the training tuples that are similar to it. So if you give an x value or y value as a nearest tuple, so it will create an unknown, or it creates one of the nearest tuple as a base, and it can be searched the each and everything surrounding of that particular tuples. So the nearest neighbor will be the sharing of all the details from the one to one. It can be identified by using the nearest neighbor algorithm. By comparing with all instances corresponding to points in an n to d spaces, the nearest neighbor are identified in terms of the Euclidean distances that are dist of x1 to x2. So the training tuples are described by n attributes. So here the training tuples are described by n attributes. Each tuple represents a point of the n-dimensional spaces. So here each tuple are represented with an n-dimensional spaces. In this way, all of the training tuples are stored in an n-dimensional pattern spaces. So whatever the data tuples are available in there, so each and every tuple will be stored with an n-dimensional space, with a space allotted to that particular distinct values. In this way, all the training tuples are stored in an n-dimensional pattern space. When given an unknown tuple, like as a k-nearest neighbor classifier, search the pattern for the k training tuples that are closest to the unknown tuple. So if you give an unknown tuple as x cube, it will search all the nearest tuples of the plus, minus, and all the things will be surrounding to that particular unknown tuple. That unknown tuple is known as a k-nearest neighbor. So these k training tuple are the k nearest neighbor of unknown tuples. So if you want to know the closeness of that particular tuple, we have a formula that is a closeness is defined in the terms of the distinct metric, such as a Euclidean distance. So the Euclidean distance between the 2 points of a tuple says as an x1 is equal to x11, x12, x13, and so on to xn. And x2 is equal to x21, x22, x23, x24, and so on to x2n. So here the x is an a. So here the x is an a tuple, and x1, x2, x3 are the n tuples. In other words, it shows the formula will be the dist of x1 comma x2 is equal to square root of n of sigma I is equal to 1 into x1i minus x2i whole square. So this is the one of the distinct formula which identify the closeness of the distinct matrix. So in other words, for each numeric attribute also we'll take a difference between the corresponding values for that attribute of the values, that is a distinction of the distance of the x1 and x2. Here the x1 is one tuple and x2 is another tuple. It squares the differences is accumulated to it. So here the x1 and x2 are the accumulated to that particular values. The targeted functions could be in the discrete or the real valued functions. So here the targeted functions are the discrete of the real and valued functions. For discrete values, we have in a KNL written the most common value among the k training examples nearest of the x cube. So here the discrete values of the KNL will be written as some other equations. The square root is taken as a total accommodated distance count. Typically, we normalize the value of each attribute So we normally normalize the each attribute before using the equation of the distance of x1 comma x2. These help to prevent the attributes with an initial large ranges, such as an income from the outweighting attributes with an initial small ranges. So we have a prevention, that is this attribute will have an initially small ranges to the large ranges, which will prevent from the overweightages or the such as an overweighting of the incomes. Minimum and maximum normalization can be used to transform a value of v of a numeric attribute a to b in the range of the 0 to 1 by computing the different values. That is, a b is equal to b minus minimum a by max a minus min a. So here the a of the numeric attributes of the normalization transform value as a b. We have the values of b with an a, normalization of the x. We have a minimum and a maximum values will be distinction in the KNN algorithm. Here the KNN we have a real value prediction for the given known tuples. It returns the mean value for the k nearest neighbors and have a distincted weighting of the nearest neighbor algorithm also. The weight of the contribution will also be weight the contribution of each of the k nearest according to their distances. We will have an query that is an x cube is equal to 1 by d of x cube comma xi of 2. Here the greatest and the weight of the closest neighbor values will be in this k nearest neighbor algorithm. We have a distinct weightage nearest to the neighbor algorithms out there, where the contribution of each k neighbor according to the distance will be the queries of the particular values. Here we can calculate that how the categorical such as a color or the different values will be assumed under that. Attributes are used to describe the tuples or all numerical values. With this k nearest neighbor algorithm, we have a maximum accuracy levels will be increased by maintaining the robustness to the noisy data. By averaging taking each and k nearest neighbors, it improves the robustness of the data values. And in the dimensionality purpose, the distance between the neighbors could be dominated by the irrelevant attributes. We have an n number of attributes are there in the surrounding places of the particular each and every tuple. That tuple will have a dimensionality between the one tuple to the another tuple, that means one attribute to the another attribute. If any attributes have multiple tuples, the tuples will have to maintain some distance. That means will have to maintain distance between the neighbors could be dominated by the irrelevant attributes, and it can be measured and it can be transferred to that particular values. To overcome it, access stretch or elimination of the at least relevant attributes will be done by the stretching process or the elimination or removing of that particular attributes. And we have a case-based reasoning, that is CBR. The CBR is used as a database of the problem solutions to solve the new problems which occurred in that particular location of that particular attribute values. And it stores the symbolic descriptions of the tuples and cases. So it's very clearly it will show that each and every tuple will have a symbolic description and gives a description of that particular tuple, not points in the Euclidean space, which are there in the Euclidean space. Those point not related to that particular tuples or classes. Here the maximum the CBR is used in the different applications. Those applications are the customer service or the legal ruling applications will be done. And we have a methodologies in the instances represented by the rich symbolic description. That is an example. Functioning graphs, search for the similar cases, multiple retrieved cases by combined, and we have a tight coupling between the case retrieval knowledge and based analysis and problem solving. So we have a few methodologies in the CBR, that is an instance represented by the rich symbolic descriptions of that particular values. The mainly CBR defines the database problem solutions, and unlikely the nearest neighbor classifiers which stores the training tuples as a points in the place spaces. When giving a new case to classify, each case-based reasoners will have to first check it an identical training case exists. If one it is found, then it is accompanying the solution to that cases is returned. If no identical cases is found, then the case-based system or the case-based reasoners will search the training cases of that particular cases having components that are similar to those of the new cases. Conceptually, these training cases may be considered as a neighbor of the new case if cases are represented as a graph. This involves searching for a subgraphs that are the similar to the subgraphs within the new cases. That cases is based on that particular values. Challenges in case based on the reasoning, including finding a good similarity or the symmetric values will be there. And we have a few challenges in the case-based reasoning. Those challenges are the find out a good similarity metrics or the identifying the index-based or the syntactic similarity measures, and when failure, backtracking or the adapting to the additional cases of the challenges of that particular CBSR. And we have another classification methods. Those are the genetic algorithms, rough set approach, fuzzy set approaches, and these are all the additional classification methods. What is the genetic algorithms? The genetic algorithms are based on an analogy to biological evolutions. An initial pollution is created consisting of the randomly generated rules. Each rule is represented by a string or a bit. So, by using these genetical algorithms, it will survive the fittest, and the motion of the survival of the fittest. A new population is formed on the consisting of the fittest rules and their offsprings. So, by using these genetical algorithms, we can create the consistency and the randomly generated rules will be done. With this, we have a rough set approach. This rough set approach will have an upper approximation and the lower approximations of the values are used to approximately roughly define an equivalent classes, or the rough set of the given classes C is an approximate to the two layers, that means lower one and upper one. The finding of the minimal subset values or the attribute values will be explained in the rough set approach. And we have a fuzzy set approach. This is one of the best fuzzy set approach, or the fuzzy logical approach. Will have to give true values between the 0.0 to 1.0 to represent that particular degree of the membership. Here the attribute values are converted to the fuzzy values, and the fuzzy values will have different categoricals. So, for example, take an income X is assigned to the fuzzy membership values. To each of these discrete values will have a low, medium, high values. For example, take as $49,000 belongs to a medium income with a fuzzy value of the 0.15 becomes, but belongs to the high income of the fuzzy value. So here the fuzzy set approaches will have different values will be segregated within a different application. These are a few other classifiers will be using in the classification methods, and with these we are completing the classification processes by using the k-nearest neighbor algorithm, and we have a few neighbor algorithms of the lazy learner. So thank you this session.